Yes, welcome to this another session. So let somebody is joining here. So today we'll continue the discussion of this pulse code modulation. In the last class, we discussed in detail about the sampling and quantization parts of this PCM. So another part of this PCM, because we have seen it consists of a transmitter separately and receiver, along with the dedicated transmission path. So today we'll see or look into the encoding part here. So encoding is nothing but simply encoding the information in terms of signal transitions. So this is important, guys, here. So what is happening here is that again it is we are trying to transform the information in terms of signal transitions. If there is a transition means what? If you are changing status from 0 to 1 or 1 to 0, you can see here. So the let us assume the original binary data could be 0, 1, 1, 0, 1, 0, 1. So this is the data we actually want to transform using encoding process. Here, for example, we are using differential coding here, a differential encoding technique we are adopting. So let us see how the things are happening here. So differential encoded data will assume reference bit will be 1. We'll assume that we'll begin with reference bit 1 here. Transition whenever is there will denote that 1 by 1, and if there are no transitions will be denoted by 0. So here you can see a good example, the same bit pattern I have taken here. We'll have to take exclusive OR between these two bits, the present bit and the reference bit or previous bit. So as the previous bit is not there here in this case, so before this what was the previous bit we don't know. So therefore we'll assume it as 1. So here you can say reference bit, same thing. 1 what we assumed is represented by high waveform, high part of the waveform. Now it is coming down because of the transition from 1 to 0. So 1 to, so here, okay, of course, the bit pattern will be different, but you can see how the coding will be done, we can understand with the help of this example. So 1 XOR 1 will get 0, 0 XOR 1, 1, 1 XOR 0, 1, 1 XOR 1, 0, 0, 0, 0 XOR 0, 0, 0 XOR 0, 0, 0 XOR 1. So like that, so here in the same manner we are getting here, but somehow you can see it is we are using non-return zero signaling in order to represent this differentially encoded data in the form of waveform. Okay. So these things are we are doing initially in the stage of the encoding process. So this is how by adopting this technique, for example, differential encoding, I took it as an example. It is adopting or based on the concept of transition. So simply you have to adopt the XOR gate, and we'll assume by assuming reference bit as 1 in the beginning, because we don't know what was the previous bit. Then we'll go on applying the successive bits here like this in this pattern, whatever it has been shown. So then we are getting differential encoded data bit stream like this. And if you want to represent in the form of a waveform, again we studied different types of coding techniques in case of encoding that we did discussion in the last class. Unipolar, bipolar NRZ, or unipolar, bipolar RZ, or split Manchester coding. So here we are taking an example of unipolar NRZ signaling. Same thing, now you can see all zeros are represented by no pulse and ones are represented by a pulse where the transition is taking place at that instant it is going to change its shape of waveform with NRZ concept. So this thing will be done in case of encoding. So remember there we took an example of differential encoding. Differential means we are using XOR gate here, and transition, where the transition is happening at that instant only we'll have to adopt this encoding technique. And while representing differential encoded data in the form of a waveform, we are using unipolar NRZ signaling. So in this way we are getting this kind of waveform. So taking the help of this particular bit stream, you have to explain in exam how you are going to get this bit stream. So that only you have to explain as the part of encoder part. Okay. So that one bit we left out there. In the last class we discussed about different techniques of encoding techniques. So in that we adopted NRZ, and differential encoding we have did in order to explain the encoding process in case of PC. So let us consider next the transmission path. Before we'll reach, now you transmitted your data, bit streams. So those bit streams are going to pass through this dedicated transmission path containing a set of regenerative repeaters. So this regeneration or regenerative repeaters is one of the very important feature of any digital system, because it is that part of the whole your transmitter and reception system, total system, where it is going to take care of your the transmission or sending your data reliably up to receiver destination. So whatever may be the length of the path. So here you can see the input what you are applying, a distorted PCM signal is applied from one channel. Like that many channels will be there, they may be multiplex and coming here it as a multiplex signal. So then it will be applied as input to regenerative repeater. It's a very important property, already I have told. It is taking care of uh, noise and distortion because of the characteristics of the transmission path. So we inviting the noise or distortion because of the properties of its own transmission path itself, or maybe due to external conditions. So these regenerative repeaters will cope up with such kind of drawbacks. Drawbacks, you can say drawbacks of the transmission path. So this capability can be well explored with the help of the regenerative repeaters as shown in the figure. So if you take one regenerative repeater, it mainly consists of three blocks here, you can see. So distorted PCM wave you are giving here, the first it will be made to pass through amplifier or equalizer. So its main duty is to shape the received pulses. Here you are getting bit stream, your information now in the form of a stream of pulses or bits. As we have represented no, in the last few slides back, how differential encoded bit stream is represented by the waveform using NRZ technique. So it is once again is going to shape the received pulses to compensate for suppose if the original shape was lost for our differential encoded bit stream, that waveform, we'll have to reshape it. We have to regain that shape back. That may be happening because of the effects of the characteristics of the transmission path, maybe the noise or distortion, which are going to affect the amplitude or phase properties of our pulses, bits of train of pulses. So that is taken care by this equalizer here. Amplifier will see that to boost the power if the power of these train of pulses got reduced. Then the shaping will be done with the help of the equalizer. Then after that, its same output, now we are going to pass it through the timing circuit here. So its main job is to provide a train of pulses to sample the equalized pulses at maximum at the instance where we have the maximum signal to noise ratio. So in simple words to tell this timing circuit what it is doing, it is taking the output of this equalizer, that is a train of reshaped received pulses, and are used to train the samples here at the instant where we are getting maximum signal to noise ratio. So why we are choosing only those instances where we have maximum SNR? It is in accordance with the noise or distortion which will be added all the way through whatever the transmission channel they have traversed. Okay. So now to cope up with that, we are doing this once again, resampling process of these equalized reshaped received pulses with the help of timing circuit at those instances where we have maximum SNR. Again, these things will be used to decide which pulses, equalized pulses, you can see again those pulses are coming here. Those equalized pulses will be decided based on, decided to go out, maybe 1 or 0, based on some threshold. So now to decide that threshold, we are using these timing circuit pulses. It has been noted here, provides a train of pulses from to sample the equalized pulses. So from equalized samples, so whatever the pulses you are getting, which are used by this timing circuitry with some delay, only at those instances where we have maximum SNR. So whenever we have or come across that instant where we have maximum SNR, then decision will be taken whether our received reshaped PCM pulse is falling above that threshold or below that threshold. If it is falling above that threshold, then it will be represented by 1 and transmitted. If it is appearing to fall below the threshold, then it will be sent as a zeroth pulse, like that. So that is how it is going to regenerate our pulses. That is the main detail, how it is going to regenerate our lost or weaker pulses, which are stream or bit stream of ones and zeros, like that. So to summarize, the accumulation of noise and distortion in this way in the repeater is completely removed. Because it is doing the equalizing, means it is taking care of amplitude distortions or phase variations because of the noise in the transmission path separately. Then using timing circuitry, we are using only those pulses, selected pulses from these reshaped received pulses at the instant of SNR, which are allowed to decide which of these received reshaped pulses will be allowed to pass as 1 or pass as 0. So in this way, in a step-by-step manner, regenerative repeaters are going to receive and retransmit our train of pulses towards the destination or the receiver. So in this way, the noise and distortion may not be allowed to accumulate anywhere on the transmission path, maybe at the receiver, completely removed. So if you don't have any accumulation of noise and distortion, that is a very important feature, guys, the key point of these regenerative repeaters. But there is a delay. That is, a regenerated signal is exactly same as original signal, but sometimes it is not, because we are using some delay, timing circuitry is there, some delay is going to happen. Or sometimes some unavoidable presence of channel noise. Whatever you can do, that cannot be avoided. Interference, that cannot be, that is unavoidable, that's what it is called. So such kind of things will causes the repeater to make wrong decisions. It may say 1 as 0 or 0 as 1. A wrong decision will be made by this regenerative repeater in case only in case of unavoidable channel noise and interference. So another thing, jitter we can call. Jitter is a common technical word. So that normally indicates, suppose the spacing between received pulses. You are going to receive the pulses here from the PCM encoder output. That spacing is somewhat some pattern supposition that it is going to follow. Suppose if it is going to deviate from that pattern, that is spacing between the received pulses from its assigned values. So that deviation of the spacing between the received pulses compared to the original received pulses is called jitter. So this results into regenerated pulse position causing distortion. Regenerated repeaters, of course, even though there is a deviation in spacing of received pulses while it is reshaping it, so deviation may occur. Even though deviation will occur, that will result into change in position, pulse position, after reshaping those received pulses from the encoded PCM pulses. That is called jitter. So these are the two main reasons here. Sometimes the regenerate signal is not same as the original signal, but that can be avoided by adopting some other techniques. So that we can see later sometime. That is beyond the scope of this discussion or syllabus. So the first operation after doing this regeneration at the receiver, now we came guys. The first operation at the receiver side you can see is to regenerate the signal. Again we have to do last one time. Of course already we did that one. This is, you can see, think of it as a last one regenerative repeater before we will hand it over to the receiver part. The receiver part will start from here, decode. So here you can see I also shown one regenerative repeater as a regeneration part. You can think of it as a last regenerative repeater throughout the all the length of the communication channel, starting from the beginning of transmitter. So then what we can do? So we have to do this reshaping and received cleaning up of these received pulses. So cleaning up from the noise and distortion due to the characteristics of the transmission path. That will be done by this final regenerative repeater. Last time you can say I have quoted. Then the stream of pulses or bits are then regrouped into code words and decoded into quantized pulse amplitude modulated signal. Means that decoding means that generating a pulse of amplitude. So we are generating pulse of amplitude or stream of pulses which are proportional or in a way so that linear sum of all pulses in the code word, one code word. It is like this, with each pulse being weighted by its own place value, like this one, binary weighted, where R is going to indicate the bits, number of bits per sample. We have to add them, all those pulses in one code. So in that way, we have to do the coding for one code word, like that many code words. So in this way, it will be, they will be decoded whole, that is a regrouping will be done. We have to do linear sum, accumulation we can call it as. So that will be done by this decoding. Then reconstruction filter and destination. Reconstruction filter we are using. So where it is going to not allowing any high frequency or noise components if they are still available, then it will be we are going to receive our. So it is something like the filter which is tuned to the bandwidth of our message signal. Only those pulses having that similar width will be allowed to pass through this reconstruction. That's what is known as reconstruction filter. Then we are going to receive our message pulses. So before we'll continue with the delta modulation, let us see. So that is over the PCM section. In the last class we started with this transmitter, and today we continued with the transmission part. That is a part of regenerative repeaters, and then we are going to wind up with this section. Next, we are going to discuss about multiplexing or TDM. So very well-known technique. So suppose if you want to transmit more than one signal types or more than one channels of information or sources of information, then the time allocated to each channel or source is also goes on reducing. So this leads to a difficulty in generation and transmission of such reduced pulses or sources. And what time interval we are allocating, no, each time or signals or information messages you want to transmit directly proportional to the reciprocal of the sampling rate. But this also has got some limitation. We cannot go on without any restriction. We cannot go on adding as many number of signals or channels or sources to be multiplexed as we want, because already I have told now, if you go on increasing the number of sources, the width or interval of time that you are allocating to each of the signal that you want to transmit it by enjoying its own time slot throughout the until it will reach the receiver is not possible. In that case, we may lose some things will start happening, because the time interval that has been actually required to be allocated for each signal to be transmitted may be not allocated. In that case, we may lose our information. Okay. So this one condition should be there, time interval that what you are allocating to each signal that you want to transmit should be reciprocal of the sampling rate. So that is one concept about the TDM. Next, delta modulation. In simple words, it is digitally representing. It is a technique where it is going to see that it is going to digitally represent your analog information sources. That's all. PCM is one technique, just now we discussed. So another technique is the delta modulation, which is also a technique where it is going to represent your analog information in terms of digits or digital. So what it is doing, it is mainly characterized with, compared to PCM, delta modulation, where the sampling frequency is purposely kept very high, so that to provide more correlation between adjacent samples of the signal, maybe with or without aliasing. Purposely it will be made. So here I have written, so the incoming message signal is intentionally oversampled, not under, oversampled to increase the correlation. This is the main intention. This is the main purpose. That's why they are going to do it intentionally, that is oversampling. Increase the correlation between adjacent samples of the signal. So in basic form, this delta modulation provides a staircase type of approximation to this oversampled signal like this, you can see. Suppose if m of t is your message signal, then oversampled delta modulated staircasely approximated signal is this. That is staircase approximation to m of t, that is mq of t. So how it will be done? Hello. Yeah, let us continue. So it is disconnected because of the network loss. So let us continue where we stopped. Let me represent this screen once again. So sorry for this technical malfunction. The network was disconnected. So we are here in basic form. The delta modulation provides staircase approximation to oversampled signal. Why it is doing oversampling already we have seen, to provide correlation, better correlation between adjacent samples of the signal. It may be having some purpose, very important purpose. So this delta modulation is going to transform this oversampled signal into a staircase approximation like this. Sorry. If here the difference between input and approximation. Input is this message signal m of t, and approximation here you can see E of NTS, it will indicate the error between sampled version of your message signal, that is M of NTS, minus and the quantized signal MQ of NTS minus TS by some time delay TS. So that error will be represented by this error or difference, you can see. The difference between the input and approximation. A staircase will indicate approximation. That is MQ. Input is M of t. M of t is input, staircase is approximation, staircase approximation. So the difference, this difference between input and approximation is quantized into only two levels, plus or minus delta, you can see. This will indicate minus delta, whatever it is coming the step size below this dotted line, it is a minus, and above that it is a plus, that's all. So if the approximation is less than signal, you can see how we are going to decide plus delta and minus delta. If approximation is less than signal level is here. So here you can take, if the approximation here you can see, here it is clearly visible. If the approximation, that is a staircase, is now more than the level. So for this pulse, we represented this by plus delta. You can see it is 1, represented by 1. And here you can see, so here it is represented by 0, because here you can see the signal level and the approximation falls below the signal level, that's why it is 0. In all these cases the approximation is above the signal level, so it will be represented by 1 1 1 1. So 1 we are using wherever the approximation is more than signal. Okay, so signal doesn't change rapidly, that will assume. If the input signal is m of t and staircase mq of, that's what I have shown here. So in this way, the delta modulation, the coding will be done. So here I have to write approximation is less than signal level. I have told approximation is less than. I have written it reversely. So it is like this. Here it is clearly visible. So I have to do that. I will do the correction. Sorry about that. So approximation here you can see it is more than signal level. Okay, that's why it is represented by 1. It is clearly visible. Here approximation is coming below the signal level. That's why it is 0. Understood? Like that. Then later this you can see the data modulation is once again resampled. This case approximation is resampled. That is error whatever you are getting using signum function. So here you can see the sampled input signal m of nts, this one staircase approximated signal, is now we are applying as input to this. So delta modulation basically consists of these two blocks, transmitter and the receiver. The transmitter part, it mainly consists of the comparator, which is going to compare m of nts with the mq of nts minus ts. This here you can see. So this equation is represented by this small section, comparator. It is comparing present sampled input M of NTS with the delayed quantized input signal. If you get an error, that is E of NTS is now applied as input to quantizer. Now quantizer, what it will do with the help, it is going to reshape this E of NTS using signal function. And its output you are getting EQ of NTS. Again it will be compared, it will be added or accumulated with this one. So that's why it is represented by accumulator here. Okay. Then its main purpose why it will be kept this accumulator in the feedback path is to see that so this accumulation should decrease, error should decrease, and once you will ensure that that will be reduced, then this will be applied as input to the encoder. So after that we are getting delta modulated waveform. Here you can see, here it is accumulator here, that is represented by this sum, this one 7.53 equation. So the same after encoding here, same accumulator will be there at the receiver, that is going to detach all the things, and it will be passed through the low pass filter to identify the bandwidth or suggest only those pulses having the bandwidth similar to the bandwidth for which this low pass filter is tuned. So in this way the delta modulation is going to work out. So detailed description we can get in the notes, updated notes that I am going to upload in the Google Classroom or in the textbook also. So this kind of delta modulation is going to suffer from slope overload distortion and granular noise. So detail about them we can discuss in the next session. So today what we discussed, a pulse code modulation we completed as a part of transmitter up to encoding we did that one, and regeneration and decoding we filtering, multiplexing and delta modulation is almost covered, and so two drawbacks we can cover along with the applications in the next session. Now we'll stop.